Hello, everyone. Welcome back to another section. Today we look at section 10.2 and 10.3, some graph terminologies and special type of graphs. Graph. So here are a few homework problems you can try. All right. So first definition we have for today is adjacent. So two vertices U and V in undirected graph are called adjacent, or in other words, neighbors. If G if there is an edge connect U and V. So the edge that connect the two vertices U and V is called incidence edge. So incident and adjacent. Okay. Another one here is the collection of set of neighbors. Suppose V in G denoted by n of V is called the neighborhood of V. Mean that the set will contain all the vertices that are adjacent to V. So that will be the neighborhood of V. All right. And another one is a degree of a vertex. So in an undirected graph, the degree of a vertex is the number of edges incident with it, except the loop at that vertex contribute to the degree of that vertex. Okay. So the loop will count 2 when you focus on the degree of an undirected graph. Okay. All right. So here's the example. Let's take a look at the degree and neighborhood of the vertices in the graph below. All right. So let's focus on the degree first. So let's start with A here. All right. So degree of A. All right. So let's count the number of edges that in incident with A. So we have 1, 2, 3, 4. And the loop count twice. I'm going to put here 5 and 6. So degree of A is 6. Degree of B, you can see 1, 2, 3, 4, 5, 6. So also 6. Degree of C, 1, 2, 3, 4, and 5 and 6. Also 6. Degree of D, 1, 2, 3, 4, and 5. So 5. And degree of E, 1, 2, 3. The degree of E equal to 3. Okay, so that's how we focus on the degree. Next one, look at the neighborhood of each vertex. So look at the neighborhood of A. So you can see here, A connect to itself, B and E. So the neighborhood of A will be A, B, and E. And then the neighborhood of B, B connected to A, to E, to D, and to C. So the neighborhood of B will combine of A, of C, D, and then E. And then the neighborhood of D, neighborhood of C first, right? So neighborhood of C, C connected to B and D. So you have B, C, and D. So the loop also count as a neighbor of C itself. And the neighborhood of D will be B, C, and E. And then the neighborhood of E will be A, B, and D, because those are the neighbor of E. Okay, so that's the idea of degree versus the neighborhood. All right. All right, next one. This is very nice theorem, the handshaking theorems. So it said that suppose we have a graph G in undirected graph, okay, with M edges. So they don't use E to present the edge anymore, but they use M. M will be the number of edges, okay? With M edges, then this is true. So 2M equal to the sum of degree of that, meaning that the sum of all degree in a graph is equal to 2 times the number of edges. Okay, so that's the idea. So here's the example. You can see, right? So suppose we have this, right? You have A, B, C, D. You can see here degree of A is 2, right? So degree of A is 2, degree of B is 2, degree of C is 2, and degree of D is also 2. So when you add them together, you get 8. And M is equal to 1, 2, 3, 4. So M equal to 4. So you see here 2M, which is 2 times 4, and that's also equal to 8. So the sum of all degree in a graph is 2 times the number of edges in the graph. So the proof is quite trivial, but I can give you one example. For example, when you think of that, this is why they call the handshake theorem. Yes, suppose you have the first person here. All right, you have one person here, and then you have another person. Okay. So they are present, let's say vertex number 1 or vertex number 2. So now if they are shake hand, then you can see that if two people are shaking hand, then they share the same edge, right? So they V1 and V2 are two different vertices, so they share one edge. So in order for them to balance, then it have to be 2 times the number of edges, right? So you can see like that. So if you have another person on the other side, so you can see here that right, if they shake in hand again, then what happens? You can see here. So now the middle person check 2 people, so the degree will be 2. And the first person and the last person have degree 1 because they only check to the middle persons. So therefore, you can see here, this is one edge, that's another edge. So now they are sharing 4 different edges, right? You can see that's what we call that the handshaking theorem because of that, right? But here's so that's a little demonstration, but here's the proof for this. All right, as you can see in the handshaking figure that I show you, each edge contribute twice to the degree count of all vertices, right? So both left hand and right hand side will equal twice the number of edges, right? As we can see in the handshaking theorem, right? Okay, so V1 and V2, when they only 2 together, then they just shake hand, right? But then when you add another one, the middle person kind of have to shake hand to 2 people. So, and then together with one hand from V1 from one hand from V3, that has total of 4 hands so far. Okay. So remember that theorem, very nice theorem to use. All right. So here is the example. How many edges are there in a graph with 6 vertices of degree 4? So in other words, we have 6 different vertices and each have degree 4. Okay, so we'll see here that by the theorem, 2m is equal summation of degree. So 2m is equal to, we have 6 different vertices, each with degree 4. So we have 6 of those, and each of that has degree 4. So you have 6 times 4. So you get 2m equal to 24. So therefore, m is equal to 12. So 12 edges. Meaning that if you want to construct a graph based on this information, you should have 12 edges, given that 6 vertices of degree 4 that you're going to have. All right. So another example, if a graph has 5 vertices, can each vertex have degree 3? So if a graph have 5 vertices, can each vertex have degree 3? Okay, so let's try again. So by the theorem, 2m equals summation of degree v. So 2m equal to 5 times 3, right? 5 vertices, each have degree 3. 2m equal to 15. So m equal to 15 divided by 2. So the answer is 7.5, which is not a whole number. So it's not possible. So it's not possible for a graph to have 0.5 edge. Right? I mean that you need to have like 12 edges, 11 edges. You can't just have like 7.5 edges, right? It's not going to be possible. So this question won't be possible. Meaning that there's no way you can construct a graph that have 5 vertices with each vertex have degree 3. That's the ideal. That's the scenario of that. Okay. All right. So next one. Another theorem, which is an undirated graph, have an even number of vertices of odd degree. Now, what does that mean? It means that if you have some vertex have odd degree, some vertex have even degree in the graph together. So if it is true, then the total number of vertices in the graph with odd degree have to be an even numbers, right? It have to be in even numbers. What does that mean? Is that okay? Let's say you can have a graph with 4 degree of odd degree. You cannot have a graph of 3 vertices with odd degree, right? So it have to be an even number of vertices of odd degree. So this is very useful when you try to construct a graph, for example. So as you can see here, it's asked us, can we construct 5 vertices? Each vertex have degree 3. So you can see here, the degree of each vertex is 3, which is an odd numbers, and we have 5 of those. It's impossible to construct. So if you have 6, then yes, but it have 5, then it's impossible, right? So this theorem number 2 also explains the second example that we see in this slide here, right? So here is the proof for that. Suppose we have 2 sets. So the first set, we collect all the degree of the vertex that are even. And the second set, we collect all the vertex that have odd degree, right? Because, you know, odd and even, you can just divide that, right? So for example, when you have 1, 2, 3, 4, 5, 6, you can say, well, V1 only collect odd number, so V1 become 1, 3, 5. And then V2 only collect even numbers, so V2 become 2, 4, 6. So similar here. So V1 only collect the vertices that with odd degree and even degree, and V2 collect the vertices with odd degree. So, and then when you put them together, you still get the whole graph, right? So here's the deal, right? So we start with the handshake theorem. It says 2m is equal to the summation of degree in that vertex in the graph. If we expand the right hand side, said now I'm gonna split them out into 2 sets. One is contain even degree and one contain odd degree. All right, so here's the deal, right? 2m is always even no matter what, right? I don't care what's m equal. You want to times by 2, you always get an even number. So what does that mean, right? It means that the right hand side, when you add them all together, it also needs to be in even numbers. because the left hand side already even, right? The only way the equation are equal if they are the same, right? So the left hand side are even, then the right hand side better be even too. So mean that the sum must be even, right? All right, so we define that V1 to be the even degree. So you can see here V1 can be 2, 4, 6, and so on. So when you sum them up, you get 2 plus 4 plus 6. This one here is 12. So always even, yes? So this guy here, always even numbers. Right? So it's always even numbers. So think of this logic, right? On the left hand side, you have even, and on the right hand side, this guy are even plus something. So can even plus odd give you even? The answer is no, right? Only even plus even give you even. So therefore, this guy must be even. And that's how we prove the theorem number 2. Okay, does it make sense? Okay, so we're using a very simple foundation here that we have. All right. All right, I hope it makes sense. Okay. So here is directed graph. One more time, we've seen it in 10.1. Just kind of bring them back here. It consists of non-empty set of vertices called the knobs, and E, the set of directed edge or an arc. All right, so it is an order pairs, right? When you see a directed edges, U, comma V, mean that it will always start at U and it's end at V. So that's the difference between directed graph versus indirected graph, right? They're indirected, you can go back and forth, but directed, it have directions, okay? Watch out for those definitions. All right. So when you have an undirected graph, when you talk about adjacent, you just say, okay, it's just, if they are connect, then you have adjacent. So it doesn't really mention which one to start with, right? But directed graph is a different thing. So it's have to have a starting point and the end point. Right? So suppose that we have UV, and then U will be the starting point, which is the initial vertex, and it is adjacent to V, and V is called the terminal vertex or the end vertex, right? And it's adjacent from U. So V is not adjacent to U, V is adjacent from U, but U is adjacent to V, right? Because the direction is very important on that. However, when you see a loop, the initial and the terminal vertex vertices of a loop are the same. Okay, so that's something to keep in mind. All right, so here we have what is called is the in degree of a vertex and an out degree of a vertex. So this is designed for directed graph. Okay, the in degree is the number of edges which terminate at V. So it's coming toward V. And then the out degree of V, denoted by D plus V, is the number of edges with V as their initial, right? So you can see one is coming to V, one is come out of V, right? So come out from V, we call that degree plus. Come into V, we call degree minus, right? All right, so a loop at a vertex contribute 1 to both the in degree and the out degree of that vertex. You can see here it doesn't go anywhere, so it come out of that and then it'll also come back into that same thing. All right, so we have here the in degree and an out degree of that directed graph that we have here. So let's take a look at the in degree first, right? So degree in degree of the vertex A. So you can see here A connect to A, so that's one. And then A doesn't go anywhere. A didn't connect to B, A didn't connect to C. So the in degree of A is only one. All right. So the in degree of vertex B, so is anyone coming to B? So yeah, D come back to B, so that's one. And then that's it. And then in degree of C, so in degree of C, so let's see. Yeah, B does come into C, so we have one here, and then D does come to C, so we have two, and that's all we have for in degree of C. So we have two, and then in degree of D, so D, yeah, so C, there's one here, and that's it, so we get one. Now our degree of A, so our degree of A, so we also have one here for that. So it does go into that, right? So you have one also, and then that's it. So I have loop, so it have one coming out, one coming in. Our degree of B, so B go to A, and then B also go to C, right? So you have one here, B go to A, and B go to C. So you have, right, there you go. So our degree of B, so you get two here, and our degree of C. So C go out to D, and then that's it, right? It's one. And then our degree of D. So D go to A here, you can see that, and then D also go to B, and then D also go to C, so we have three. There you go. Right, so that's the idea that we have for that. Okay, sounds good. Right, so check one more time. So in degree of A is one, in degree of B, there's one there, and in degree of C, there's one go to C, that's two. In degree of D, there's only one go to D, so it's one. Our degree of A is one, our degree of B is two, our degree of C is one, it's only go to D, and then our degree of D will be 3. There you go. So D go to A, D also go to B, and then D also go to C. So that's the idea for that. All right. All right. So suppose we have a graph G with V and E. So again, E is a number of edges with directed edges. Then the absolute value of number of edges equal to the summation of in degree of V and also equal to the summation of in degree of our degree of V. Okay, that's the idea. So the first sum count the number of outgoing edges over all vertices, and the second sum count the number of incoming edges over all the vertices, right? So both sum equal to the number of edges in the graph. Right? You can have that. All right, so here's some special graphs that we have. First one is complete graph. So we denote it by k sub n, right? So complete graph is k sub n. It is a simple graph that contains exactly one edge between each pair of distinct vertices. Again, complete graph is a symbol graph, right? And we did talk about the symbol graph in section 10.1. So here is, few example of complete graph. So K1 only 1 dot, K2 is 2 dot, K3, K4, K5, and K6. All right. All right, so that's complete graph, right? So each pair of vertices will be connected by one edge. All right, so you can see here, K3, we have 3 vertices and they all connected one at a time, right? So the K4, every edges connected, right? K5, every vertices are connected by each pair of single vertices, right? One edge only, right? There's no multi-loop. That's what we call symbol graph, right? There's no multi-graph. Another one is cycle and wheel. So cycle is a simple graph where it doesn't have to connect all the vertices together. So this is kind of different from complete graph. So this is just a cycle graph, right? So it's kind of a cycle you can think of, right? You can see on the graph. And another one is a wheel. So wheel is just add another a vertex in the middle and connect the all vertices together. We get a wheel, right? So here you go. It's a wheel kind of modification of a cycle. So you can see here, this guy on top, we can just put the dot in the middle and then reach out to everyone. So we have a wheel. So for W4, W5, W6. So those are the special graph that we have. All right, we have complete graph. We know by K sub n. We have a cycle denoted by C sub n, and then we have a wheel denoted by W sub n. Now one which is pipeptide. So this is quite nice. So if you take a look at the definition, it's a bit abstract. So technically, a graph is pipeptide if we can partition V into 2 disjoint subset V1 and V2, such that every edge connect a vertex in V1 and a vertex in V2. So we can split them out into 2 subsets, but then they still connected from one set to another set. Okay. However, if the element in the same set, they cannot be connected. So if that's the case, then we have ourselves a pipeptide, right? It can connect to the other set, but it's not allowed to connect with itself, right? For example, if we have 2 groups, the people in the group cannot communicate with each other, but they can talk with the other people in the other group. Okay, so that's the idea of pipeptide. So here's the example, right? You can see, right? V1, V2, V3 in the same set, so but then they're not allowed to talk to each other. So that's why they're not connected. V4 and V5 is the same thing, they are not connected, but V1 and V4 are connect, and then V5 and V3 and V2 are connect, right? So that's the idea of pipeptide. So it's sometimes it's hard to deal with a big graph. So we have a theorem which is kind of nice to use. We call that the color theorem. All right. So, and this will make the procedure of showing a pipeptide much easier. So we use 2 colors, red and blue. All right. So if you just put start randomly with any vertex, and you put a color red or blue, and then the next vertex adjacent to that cannot be the same color. So if they are connected, they have to be a different color at each other. And if you don't see any contradictions, then it is pipeptide. But if you see a contradiction, which is 2 adjacent vertices have the same color, then that's not a pipeptide. All right. So that's how we use to prove or to show something as pipeptide, which is easier than use the definition of pipeptide. So here is the example that you can see. All right, so let's see if I can do some color here. So let's start with A. So A will be red. And because A is red, B cannot be red, so B have to be blue. And because A and B are adjacent to each other, they have to be different colors. And now adjacent to B is C, so because B is blue already, so C have to be something else, so C have to be red. All right, and then adjacent to C is D, so C already red, so D have to be blue. And adjacent to C is also E, and C is red already, so E have to be blue. You can see here we don't have any contradiction because A and D are adjacent and they are the opposite colors. A and E are adjacent, so they be opposite color. You can see B and E, they are both blue, but it's okay because they are not adjacent to each other. So B and D are both blue, it's okay because they are not adjacent to each other, right? So therefore it is pi peptide. So this graph is pi peptide. So now, we can create two sets, right? So V1, you can pick any. So V1 will contain C and A, okay? And then V2 will contain B, D, E, B, D, and E. So now you can see it's the same graph, but we just kind of present things differently. So A connect to B, so A connect to B, and A also connect to D. All right, and then A also connects to E. There we go. And C connect to B, and C also connect to D. There you go, right? So that's how we show something as pi peptide, and that's how you present it. So that would be your solution. So make sure when you do your exams, and this is how you show is this pi peptides, okay? So second example, so again, you can start with any color, right? So I start with A is blue. Let's see what's the neighborhood of A. Neighborhood of A will be B. So B have to be red, and A also have D as neighborhood, so that's also be red. And then A and E also be red because they are adjacent to each other. All right. So now next we look moving on. So B, now the neighbor of B is A, so A is blue, it's good. And neighbor B is C, so B is red, C have to be blue. So there you go. And then B is red, so F also need to be blue, right? Because F is a neighbor of B. But now you can see the focus here between F and C. So F and C are neighbor, so they need to be different color. But they are both blue. So the graph is not pi peptide. By the color theorems. Okay, so that's the idea. Right, very straightforward. All right. All right, another example is so that C6 is pi peptide. All right. All right, here you go. That's C6. Yeah, you can easily show that using the color theorem to do it. But this is how we kind of show it using the definition. So we partition into two sets, V1, V3, V5. So you can see here randomly, right? V1, V2, V3, V4, V5, and V6. So we partition V1, V3, V5 together, and then V2, V4, V6 together. And then you can, kind of make a separation. And you can see here the two sets we have, V1, V3, V5, they are not connected. And then, however, they are connected to vertices on the other set. And that's the reason why they are pi peptide, just how we kind of using the color theorem to show it. And now C3 is not pi peptide. You can see there, it's kind of contradict the color theorems. But then you want to use the definition to prove it, then you can see here there's no way we can partition into subsets so that they are not connected. All right, so that's another example that you can see. One is pi peptide, one is not pi peptide. Now another one we have here is complete pi peptide. So here we have pi peptide, and then we have complete pi peptide. Okay. So complete pi peptide means that every vertex in set V has to connect to every vertex in set V2. All right. So if that the case, then we have complete pi peptide. So we use K, M, comma, N to denote the complete pi peptide concept. So here we go. So K23, this is the complete pi peptide. And you can see here, this set have two vertex, and then every is connect to every single vertex in the other set. So they all connected, right? So this is K33, and then K35, and then K26, right? So depends. So you can see here, suppose we have two dots here, and then three dots over here. So you can have, okay, that's connected, and that's connected. All right, so you can think that, right? This is only pi peptide. So this is only pi peptide. But this one here is complete pi peptide, right? That's the difference. So pi peptide, it doesn't have to connect everyone from one set to another set, as long as it's follow the definition. But complete pi peptide, every one is connected from one set to another set. So pi peptide graph I use to model a lot, right here. An example like job assignment, you can use that. So each vertex can present an employees, and you will have an independent job that each employee can do. So you can use that as a model. So here's the example, right? Two examples, for example, Elvis, Pekovic, Chen, and David. So those are the employee. And then, Elvis can do requirements. Elvis can also do testing. And then Bekovic can do architectures, can do implementation, and can do testing, right? That's the idea. So, you can use that to model uh, job assignment, things like that, right? Just like, when you do a group project, you have 3 people and you have ton of assignment to do, then you assign each person do certain project, but then you can see that person A don't connect to person B, right? They're all independent from each other, but they do assignment on the side, right? So very nice. So another one here we have a subgraph, which is a graph that came from the original graph, right? So we have K5 and then the subgraph of K5. So meaning that If a vertex is in your subgraph, it's better be in the original graph, right? So that's the idea. So So you can see here, I have a vertex E here. We have vertex E here. I have a vertex A. Original one also have vertex A. And in here, A and E are connected. Over here, A and E better be connected. So so we can have G, G here and then H here. So H is a subgraph uh, of G. But if I also have something very similar like this, right? Very similar. Let's see here, but we call that X, Y, Z, and W. So call this one K. So K is not a subgraph of G. Okay, even though you can see K, the graph K, and the graph H are very similar, but K is not a subgraph of G because X belongs to K, but X does not belong to G. Versus over here, E belong to H, and then E also belong to G, right? So they have to maintain that position. So you can see here, X and Y are connected, but there's no X and Y in the graph G. So K is not a subgraph of G, even though it has similar shape as the graph H, right? So watch out for those little details, okay? So unions of two graphs. So you suppose you have two graph that have vertices connect in some way, then you can put those two graphs together in one graph, but you still maintain the connectedness of the vertices itself, right? You can see here, so B and C are connected, B and E are connected, and then B and F are also connected. So when you union together, you still have those connections to be focused on. And you can see here D and F are not connected, and put a union together, D and F are also not connected. So that's the mentality when you do a union, right? All right, so you would not change anything if you separate them. Just put one graph so they don't have to deal with multiple terms. And another section we have here is 10.3. This is different way to present graph, and this is called graph isomorphisms on this. All right, so here's a few examples that you can try, a homework problem you can try on. Yeah, I'm gonna do this in a little bit